So let's check example 1. You enter a chess tournament where your probability of winning several types of the players, we call them type 1, type 2, and type 3. So for type 1, you have pawn 3 against the player, and pawn 4 against the quarter of the type 2 players, and pawn 5 against the other type 3 remaining players. So you play a game against a randomly chosen opponent. What is the probability of winning? So first look, it might be far away. You feel like there might be a little gap to understand the total probability theory we discussed before and between this example. Okay, let's try to establish the framework. Okay, try to get close to the total probability theory. Now you can think about all those players. Okay, you can think about all those players using a Venn diagram. So for all the players, okay, you can divide it into several types, right? You will notice that this is half of the player, which means 50% of the player. We call it 50%, okay, 50%. So 50%, you call it type 1. Yes, type 1. So this is type 1 player, 50%. And a quarter of the player you call type 2. And the remaining players you call type 3, right? Type 3. So you divided all the players into 3 types, right? Into 3 types. And those probability 0.3, 0.4, 0.5, it's given for you win for each type of the players, right? That is not the probability you win, okay? So you can define, okay? You can define in this way. Now, let me help you establish the framework and get close to the total probability theory based on example 1. So we will let event B, okay? Be careful about the notation I use, event B and those event A, those partition event. So event B will be you win the game, okay? You win the game. You win the game. And we don't care about what is the component you had. So that is the question asked. What is the probability of winning? You had a randomly chosen opponent. You win the game. Okay? So that is the probability B we are looking for. Okay? Probability of B we are looking for. But we should establish the framework as a total probability theory to check that. Now, how can we understand those numbers 0.3, 0.4, and 0.5? So if you can read this one, you can read this statement as your probability of winning a game is 0.3 given the condition your component is type 1, right? You can understand this statement in this way. Your probability of winning a game is 0.3 given the condition you have a type 1 opponent, right? So I will call the event. I will let the event AI, okay? I will let the event AI means you have the type I component, okay? So I will let the event AI as playing with opponent. of type I, okay, of type I. So here, what are the event A1, A2, A3? So it's similar like here, okay? It's similar like here. You divide your opponent into three types. Type 1, type 2, type 3, right? Type 1, you have 50% of the opponent. Type 2, you have 25%. And another type 3, you have also 25%. So this 50% means you playing with the opponent in type 1. And this is the type 2, and this is type 3, right? So you are only have the opponent in all those type 1, type 2, type 3, and you can only have the opponent from either one of the type. You cannot have one opponent which come from both type 1, type 2, right? So this opponent you will have, that is come from only one type. So here actually the event forms a partition, okay? This event forms a partitions, okay, of the sample space. So partitions, okay? Partitions which implies AI intersect AJ AI intersect AJ are null event for any I not equal to J. And number two, the union, okay? The union of all those, that gives the sample space, which means all the players, okay? All the players, sample space, okay? Sample space. And you will have the event B, okay? Event B, you win the game. You win the game. Now, how can we understand those number again? 0.3, 0.4, 0.5. So this one, okay, this one we can read it as the conditional probability. So the probability of event B, you win the game, given the condition your opponent is type 1, your opponent is type 1, which is A1, that is 0.3. Right? How can we understand these conditional probabilities? 0.3. So that is you win the game. Let me write the statement. You win the game with the probability, right? The probability you win the game. Let me mention the probability. Okay. Let me mention the probability. So how can we understand this number 0.3? The probability you win the game given the condition, given the opponent comes from type 1. Type 1, right? And then so far you can write the probability of winning the game given the condition your opponent come from type 2 will be 0.4. And the probability of winning the game given the condition your opponent come from type 3, that will be 0.5. And according to the total probability theory, okay, let's recall the total probability theory. If n is 3, the probability of B can be written as the probability A1 intersect B plus A2 intersect B and plus, B, and then plus A3, probability of A3 B. But we can rewrite the AI intersect B as conditional probability, right? As conditional probability. Let me write just the Riemann sum here. So for AI intersect B, you can write the probability AI times the conditional probability of event B giving AI. My I is the index starting from 1 to 3, right? So here we have already figured out the conditional probability, right? The probability my event B is winning the game. So we have already figured out what does those 0.3, 0.4, 0.5 means. That is the probability of winning the game when I have the opponent from type 1, type 2, type 3, right? And then we need those P probability of A1, A2, A3, right? So what does this one mean? What does this probability A1 mean? This means playing with opponent from type 1. If you have the chance to playing with a player from type 1, what is the probability? You have half of the players come from type 1, right? Half of the players. That is the partition we already understand, right? According to this Venn diagram, we know probability, and you have this type 2 players as the opponent. The probability is a quarter. And you have the probability, you have the component from type 3, the probability is also a quarter, the remaining quarter. That is how we understand the partition, okay? The partitions for all the players. Now it will be much easier to understand the probability according to the total probability theory, okay? According to the total probability theory, you can rewrite in this way, okay? Total probability theory, since the partition n equals 3, you have I starting from 1 to 3, then you have the probability AI intersect B. How can you rewrite AI intersect B probability? So that will be probability of AI. Let me rewrite here, okay? Let me rewrite here. So that will be following the formula here. The probability of AI times the conditional probability B given AI. So this example is much straightforward to form the framework as the total probability theory. So will be PA1 0.5 times the conditional probability. The first one is 0.3, and will be the second one PA2 times the conditional probability 0.4, and will be the third PA3 times the conditional probability 0.5, and the final answer. Let me check. The final answer will be 0.375. Try to take notes, okay? Try to take notes for this example, and how we applied the total probability theory, okay? How we apply the total probability theory. Now let's start with example 2, okay? With example 2. And actually there is the spatial partition. Okay? Let me just mention to you. Actually, there is the spatial partition if you have another event, okay? Spatial partition. You can also take it as A1, okay? So for example, event A. For event A, I'm not going to call it A1, A2, AN. For event A, this is also a sample space, okay? Go previous page for 1 minute. You check the video later, okay? Check the video later. Let me explain here. The special partition for event A, you can do A intersect its complement. That is null event. And A union its complement. That is a sample space. I think I mentioned this formula before. Okay, I mentioned this formula before. So actually A and A's complement, they are partitions. Okay, they are partitions of the sample space. So you can let A as A1, A's complement as A2. So for any subset of the sample space event A, you can write in this way. Okay, you can write this way. Let me go back a little quick. Some people want to take note. Okay, so try to take note. Okay, try to take note. And we will analyze the example 2. Okay, we will analyze example 2. I think we don't have enough time to finish the Bayes formula today. So can you catch up? Are you done with the note? Now let me continue, okay? Let me continue. All right. So here, when the partition, when we mention the total probability theory, we will mention the partitions A1, A2 until AN. And here there is the special partitions, okay? Special partitions. Once event A and its complement, they forms partitions, okay? They forms partition because event A and its complement, the intersection gives null event. The union gives the sample space. So this is the special partition. You can write in this way. The A1, we would like to write the partition as A1 until AN. So the partition will be 2, okay? 2 when my n is 2 in this way, okay? In this way. A and A's complement. Now let's read the example 2. An insurance company believes that people can be divided into two classes: those who are accident prone and those who are not. Right? This is also like a partition, right? People are divided into two classes: those who are accident prone and those who are not. Event A, people are accident prone, and its complement will be who are not accident prone. The company's statistics show that an accident prone person will have an accident at some time with a fixed 1 year period with probability 0.4, whereas this probability decreased to 0.2 for a person who is not an accident prone. If we assume 30% of the population belongs to this accident prone, what is the probability a new policy holder will have an accident with the year of purchasing a policy? So here, it's very clear, okay? It's very clear. We are going to divide. Let me write the event first, okay? Let's define the event first. So let event A, okay? Let event A as the people who have the accident, who are accident prone, right? So people who are accident prone. People who are accident prone. And then what is the A's complement? A's complement, which means people who are not accident prone. And of course, you can take this one. You can take A and A's complement as A1 and A2, right? A1, A2. And here, if you understand the partition, there is no need to write. There is no need to mention their partitions because we already understand it. Okay, we already understand it. Now we are going to write the partition. Okay, we are going to write the partition, and we're not so sure about the percentage. Okay, let's read the question one by one. So this is A. This is A's complement. Okay. Of course, the people who are accident prone will be smaller proportion, right? Now let's read what does the probability mean. Okay, they are talking about the accident prone with the time period, one fixed year. Okay, a fixed 1 year, a fixed 1 year. Now let's try to understand. And by the way, what is event B? What is event B? Event B means people have an accident, right? A person have an accident. So that is a person have an accident. So that will a person have the actual accident, have has an accident. What is the probability we are interested? We are interested in the probability B, right? What is the probability that a new policyholder will have an accident within a year of purchasing a policy? Within a year of purchasing policy, that is the time period the company considered, right? So a person has an actual accident. We are interested in the probability of event B. But what does those point 4 and point 2 mean? Let's read it. The company's statistics show that an accident-prone person, given this person is accident-prone, they belongs to event A, that will have the actual accident. The probability is 0.4. So that means given the person belongs to A1, right? A1 belongs to this type. What is this type? Given this person is accident prone type, A1, or I just write A, okay? It will be much easier to write A, and we understand A1, A2, their partitions, right? So given this person is accident prone, and then the probability of having an actual accident is 0.4. And then if the person is not an accident prone, of course it makes sense. If the person is not accident prone, then the probability of having an accident will be decreases to 0.2. It makes sense, right? It makes sense. And I think you, with the common sense, you understand what is the accident prone, right? Accident prone, like people would people some people they would like to take a risk after they drink wine. Okay, some people they are more conservative. They never drive when they drink wine, or they never drink when they are going to drive the car. So the probability of having an accident when the person is not accident prone, then that is 0.2, which will decrease the probability, right? Now Now, according to the total probability theory, okay, let's recall the total probability theory. Since we have two partitions, now it becomes much easier to represent the total probability theory. That will be PA1 intersect B plus A2 intersect B, right? And how can we write the intersection? How can we express the intersection as a conditional probability? PA1 times the conditional probability P giving A1, okay, A1, and plus PA2. If you understand the logic of total probability theory, then it will be a little quick, okay? It will be a little quick to expand it the formula, and you have it's required, okay? It's required. Then you can understand the Bayes formula later, okay? You can understand the Bayes expression later. So given those partitions, right? In the total probability theory, it's giving those partitions as a conditional event. Now here we have already figured out those. So we need what we need here. This here A1 means the event A. A2 means A's complement. So I need the probability of A and the probability of A's complement. What does probability of event A mean? What is the probability of the people who are accident prone? What is the percentage of the people's populations who are accident prone? If we assume that 30% of the population is accident prone, pretty easy, right? 0.3. How about the percentage who are not? Of course, 1.7. And how can we get 1.7, by the way? How can we get 1.7 here? Because 1 minus probability of event A, right? In this one, you can work out the probability of A's complement. So that means the partition, okay, the partition for the population, 30%, okay, 30% they are accident prone and 70% they are not accident prone, right? That makes sense. We divide the people into two classes, that is the partition. Now it will be much easier to work out the probability of a randomly selected policy holder who have the actual accident. That will be according to my formula, okay? According to my formula, I record the formula there. So that will be probability A's complement times probability event B giving A's complement. Now the calculation is pretty simple, right? 0.3 times 0.4 plus 0.7 times 0.2, and then the final answer will be 0.12, 0.14. So 0.26, right? 0.26. So a new policyholder will have a accident. The probability is 0.26, okay, 0.26, which is a little higher, than this conditional probability, but a little much lower than the probability when we know this person is prone. So here actually we don't know what is the type for this policy holder, okay, policy holder. We don't know whether this policy holder is accident prone or not, but the probability, okay, the probability of this new policy holder without the information we know accident prone or not, the probability of having an accident will be 0.26, okay, 0.26. So that is example 2, okay, that is example 2. So are you done with the note? Are you done with the note? Please give me feedback. Can anyone follow me? Okay. Let's continue, okay? So try to understand the total probability theory, and we are only deal with the 2 or 3 or at most 4 partitions, okay? But we give the total probability theory when we have the partition A1, A2 until AN. So to deal with the examples, that will be much easier. But be careful to define your partitions and the event of B. Then after you establish those framework and figure out the probability for each term, then it will be easy to work out the final answer. That's why we need the total probability theory, okay? Now let's check what is Bayes' rule. And Bayes' rule is named by English philosophy, Bayes, okay? There is some historic story about him. You can search in Google. So let A1, A2, AM be disjoint event. Now we understand what are disjoint event, right? That form a partition of the sample space. So no problem. We understand those, right? And assume that the probability for each partition is greater than 0. Yeah, that is also the condition we should satisfy when we talk about the total probability theory. Then for any event B such that now for any event B, we know the probability of B is positive, which means event B is not the null event. Then we have this one. Be careful, okay? Be careful. This is the new conditional probability we are talking about. This is the new one, okay? This is the new one. This is given the event B, the event B occurs, then the probability of event AI. Then what is this one? Okay, what is this one? Now let's rewrite it. Okay, let's rewrite it. According to conditional probability. Again, as I said, this is different from the one we are talking about in the total probability theory. This is event B occurs, and then the probability of some partition event AI. So according to the definition of conditional probability, this conditional probability will be AI over AI probability AIB intersect probability of AI intersect B over probability of B according to conditional probability definition, right? Definition. Let's figure out one by one, okay? Let's figure out one by one. Now, what is this one? What is this intersection? We can rewrite another conditional probability, okay? We can rewrite another conditional probability. This is the one we are familiar with in the total probability theory, okay? This is the one we are familiar with. Given the event AI, occurs, the probability of event B, we know according to the definition again, that is BAI over probability AI, right? That is, both of those are according to the definitions. Now we can rewrite the intersection. Or rewrite the conditional probability in this way: probability of AI times probability B giving event AI occurs, right? So here probability of AI intersect B, probability B intersect AI, they are the same, right? They are the same. So this one we can replace AI intersect B according to this one. This is some conditional probability we are familiar with in the total probability theory. And this conditional one is a new one, okay? Is a new one. So the intersection AI intersect B probability will be probability AI times the conditional probability event B giving AI. Be careful, okay? Be careful. Those two conditional probabilities, they are different. Now, what is the probability of event B? According to total probability theory, we know the expansion, right? We know the expression of the probability of event B. What are those? According to total probability theory, we know it's A1 times the probability event B giving A1 plus the last one. And here again, it's M partitions, right? We have the M partitions. Giving an, and it will be much easier, okay? It will be much easier to understand the Bayes rule when my n is 3, okay? For example, when n is 3, which means we have 3 events, okay, A1, A2, A3 as the partition of the sample space. Here the I means for any I, okay, for any I you choose from 1 to 3. So AI given B, that will be probability of AI times the probability B giving the event AI, and over the probability PB, okay, over the probability B. What are these B? So will be PA1 times probability B. Let me expand it again, okay, So a little confusing, okay, a little confusing when we add the Bayes rule. Try to figure out, okay, And let me expand it, the probability of B. Let's keep the top, okay? And we understand how we get the conditional probability. We just rewrite the probability of AI intersect B. And what is B? What is probability of event B? So that will be according to total probability theory. So the denominator event B, how we rewrite the probability of event B, that means we that follows the total probability theory. So will be B giving A1 plus PA2 probability B giving A2. Let me shift in here. A2 and plus probability A3 times the conditional probability event B giving A3. So you can write by yourself, okay? You can write by yourself how we expanded the probability of event B when we have the n is 3. We have 3 partitions, okay? 3 partitions, 3 events as the partitions for the sample space. To expand it, to rewrite the event of B, we follow the total probability theory, okay? We follow the total probability theory. And how we understand why we need this probability, why we need to work out or evaluate this conditional probability given the event B occurs, okay, given the event B occurs, the given the event B occurs, then we get the partitions, right, the probability of the partitions. So here, according to the previous example, okay, let's try to understand what is the probability. What is this Bayes probability here, okay? So for the Bayes rule, we need to understand what is this one, right? For example, my I is 1, okay? When I give my I, when I is 1. Based on this example, okay? When I is 1, what is the probability? What is this conditional probability? So that is the Bayes rule, right? That is Bayes rule. But how can we understand? So this one means a person. How can we understand this conditional probability? Let's check that. Given the condition, a person has, or a new policyholder has already had an accident, right? Giving a new policyholder had an accident, then we know this person belongs to the accident-prone type probability, right? And we from the common sense, we understand that if a new policyholder had an accident, the person belongs to the accident-prone probability will be higher than the person who belongs to not accident-prone type, right? So this one means this combines with the statistical inference part. So it's like we already know the person have an accident, and this is something easy to observe in the life, right? Observe with the real situation. We observe a new policyholder have an accident, but what is the probability this person is accident prone? Or if a new policyholder had an accident occurs, what is the probability this person is not accident prone, right? That is the question usually we're interested based on this example. That is the probability the insurance company will be interested if a new policyholder have an accident. What is the probability? What is the probability this person is accident prone? If this conditional probability is much higher, then we can guess that the insurance company will charge the rate fee for the people who are accident prone much higher than the customers who are not accident prone. So that will this probability actually will make some statistical inference, which will help the statistical company to make will help the insurance company to make a decision, right? Make a decision. So they will charge the if a customer is coming, he want to buy the policy for 1 year. If they can classify this customer as an accident prone, they will charge higher than the customer who are not accident prone. So this is very interesting topic, and I guess from the Bayes law and the total probability theory, we are going to understand why we need to study those probability. Okay, why we need those probability in the real situation. How can we make a decision based on the number, based on the probability you calculated? So that part based on the probability you had, based on those information you had, you make a decision that belongs to the inference. Okay, that belongs to the inference part. It will be very interesting topic. Okay, so that's why I start this section in this way. We give the total probability theory first, and then we are trying to understand. So this looks like a much more theoretic. Okay, just the probability AI given the condition the event B occurs, how we rewrite this probability. So this gives a formula how we evaluate this conditional probability, and this is called the Bayes rule. Okay, Bayes rule. Now let's check next. How we interpret. Okay, how we interpret the Bayes rule. Okay, so let's read this one a little bit. Okay, understand the interpretation of the Bayes rule. So we observe a shade. Okay, we observe a shade in a person's X-ray. This is called event B. Okay, this is called the effect. Okay, this is called the effect. And we want to estimate the likelihood of three mutually exclusive and collectively exhaustive potential causes. Okay, a person's X-ray. If it's cause 1, that means the shade was there is a malignant tumor, and cause 2 there is a non-malignant tumor. Cause 3 will be some other reason than a tumor when you saw a shade in a person's X-ray. So there will be three causes here. We call it event A1, A2, A3. Okay, and of course they form the partition. Okay, they form the partitions for the reasons to explain the shade for a person's X-ray. Right? The first cause is a malignant tumor and non-malignant tumor and rather than tumor, right? So we assume that we know those probability. So usually we know the probability for each event, right? For each event A1, A2, A3, like what is the percentage for the in the hospital. Usually when the doctors review the X-rays, they got some basic information. Okay, they have those knowledge before. Actually they know usually what is the percentage if the shade looks like a tumor, right? Malignant tumor or non-malignant tumor or some other reasons. They know this probability AI. And what does this probability, okay, what does this probability mean? I think with this example, with this scenario, it will be much easier to understand this probability. For example, when I is 1, okay, when I is 1, that means given the given the shade given the shade oh sorry given there exists a tumor, then we can observe a shade in the X-ray result, right? Giving for the patient, okay, actually it's for the patient, giving there exists a malignant tumor exist. Given there exists a malignant tumor for the patient, for the person, the probability of the event, the probability of the shade shown in the X-ray, the probability of the shade shown in the X-ray, right? Or you can also understand the probability of event B giving A2. That means given there exists a non-malignant tumor for the person, the probability of the shade shown in the X-ray. And we know, actually, we know, if we assume we know those two probability, then what does this one mean? What does this event mean? So what does this conditional probability we mentioned in the Bayes rule? So that means we see a shade, we observe a shade in the X-ray. That is more direct in the daily life, right? Because sometimes when the doctor gives make a decision, how can they make a decision? Sometimes they don't know actually whether actually it is a tumor or not. They just check the results. They just check the X-ray, whether have a shade from the X-ray for patient, right? So they read the X-ray, the how we call that? It's like photos, right? X-ray photos. So the doctors will read the X-ray photos, and then the doctor observe a shade in one person's X-ray photos, and then the doctors is going to inform whether this shade belongs to event A1. Is this shade a malignant tumor or non-malignant tumor or something else, right? He is going to check the probability, right? And this probability is important, right? If the probability, if this probability is high, A1, if we observe a shade for a patient in the patient X-ray photos, and it belongs to a malignant tumor, if this probability is higher, that might imply it's like a cancer, right? It might be a cancer. So that is a higher probability. If the probability for conditional probability given event B, the shade observed, but A3, the probability of A3 is much higher. Maybe it's something not so important, not so related to the cancer. Make sense? So actually, this part has a very close relation to the um, biomedical statistics. Okay, biomedical statistics, and they have widely application for the Bayes rule. Even though it's confusing, but if you think about the special case, it will be interesting to talk about it. Then how you evaluate the conditional probability for the Bayes rule? So this one will be AI intersect B. How can you rewrite the numerator AI intersect B? So this part actually is the probability. You just rewrite the conditional probability first, right? What is the conditional probability given B with AI? So will be AI intersect B over PB. So we expanded for PB. This is the case when we have the partition A1, A2, A3. So this part actually is probability of PB. You just expanded probability of event B with the total probability theory. And the top, the numerator, you just rewrite another conditional probability, right? Another conditional probability, and we assume we know that. Okay, we know that. We assume we know those probability, and that is some probability we can form based on the knowledge of the doctors, and then they can make the decisions. And finally, you will notice that it's a probability, right? Even though maybe the shade observed and the probability, the causes 3, it's something else rather than tumor. Even though this probability is 95%, but finally maybe the person will still be diagnosed by a cancer. So we know that the probability is just by chance, right? It's not 100% correct decisions we made. Okay, so it will be the interesting two rules. Okay, one theory and one rule in this section, and we will continue more examples next time. Okay, since I got a little problem at the very beginning, so we got a little delay. So we stop here today.